Hello everybody. So today we're going to start working into chapter 4, which is going to be calculations and the chemical equation. So a couple things you should know prior to starting this section is going to be basically how to read the periodic table, understanding how many electrons there are for each atom, and to understand how many valence electrons are there for each atom. Reading the periodic table and figuring out the atomic mass for that element, and of course when you review the periodic table, understanding what the atomic symbol is for those atoms and being able to identify them. All right, there's no need to memorize these. I mean, obviously, why? It's because we can go to the periodic table and check these all out. We have electrons, symbol, name, atomic mass. It's not a big deal. You will always have one of these available, so review and check it out. Don't hesitate to use it. So what we're going to start on is what the mole is and how that relates to atoms and the periodic table. So first off, the atoms are exceedingly small. So what does that mean? Exceedingly small. The atoms make up everything. No, they don't lie. What I mean is that everything that we use, everything that we interact with, is made up by a smaller particle or building block, which we call atoms. For example, I have a can of soda over here. This soda just happens to contain 39 grams of sugar. Well, the sugar we know is the sweet part, right? Well, in that sugar is made up by atoms. Specifically, it's made up by 12 carbon atoms, 22 hydrogen atoms, and finally 11 oxygen atoms. When we combine those in the right way, we create sugar. If we combine them in a different way, we will get a different molecule. Okay? So later on, something I'll ask you all to do is figure out how many molecules of sugar are there in a can of Coke. But we're getting a little bit ahead of ourselves. Okay? So atoms are exceedingly small. They are used as a unit of measure, and that unit of measure is known as the atomic mass unit, or AMU. AMU is defined as being 1/12, all right, 1/12 of an atom carbon. That's equal to 1 AMU. So what does that mean? Well, if I were to have one carbon atom, and I cut it up into 12 parts, right? And I took one small part of that, which is 1/12, that is equal to 1 AMU. If we go to our periodic table, you see over here that carbon weighs 12 AMU. So that gives us an easy way to be able to give a relationship of mass between the different elements in our periodic table. And we can use that, and we do use that system to figure out many things. Like, for example, here, what is the atomic mass of one atom of fluorine? Well, the answer is 19. When we go back and check it on the periodic table, fluorine weighs 18.998 AMU. I mean, we round that up. This is more or less equal to, 18.998 AMU. So one of the good things that we're now able to define is a relationship between AMU and grams. Okay. That was given to us up here. It says 1 AMU is equal to 1.661 times 10 to the negative 24 grams. So now we're going to take it from this arbitrary unit of AMU, which is, remember we defined this is equal to 1/12 of a carbon atom, and then we can readily convert that into something we work with on a much more frequent basis, which is mass in grams. Right? So here we're going to start off with, okay, we need to figure out how many grams of fluorine are in, one atom of fluorine. Right? And so for any measurement, if you recall, every measurement has a number and a unit, right? So here we start off with our first part. We have for every 19.00 AMU of fluorine, this is equal to 1 atom of fluorine. And the next step is we need to go from atoms or AMUs of fluorine, okay, and we need to figure out what the mass relationship is. So our conversion factor we already know that's going to be 1.661 times 10 to the 24 power times 10 to the negative 24 power grams, and this is equal to 1 AMU of fluorine. Okay. Well, we're looking for grams per atom of fluorine. All right. So when we set this up, we need to make sure and do this that way the AMU cancel out, and the only thing we're left with is going to be grams and atoms of fluorine. So when we calculate this, our answer should come out to be, as it states there, 3.156 times 10 to the negative 23 grams of fluorine for every 1 atom of fluorine. Okay. This is an easy way to be able to convert, like I said. But we don't usually deal with single atoms. We usually deal with thousands, if not millions or trillions of atoms. Okay. So we have a way to do that. That's that unit first. But in order to be able to work with that large of a unit, we need to be able to have a way to make another relationship. This relationship is known as the mole. The mole was defined as being equal to 6.022 times 10 to the 23rd atoms. Here it is specifically designed or defined as 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. Does it have to be just atoms? No, absolutely not. We can define a mole to be anything. It can be any particle or any unit you want to define. Alright. And the shorthand way of writing 6.022 times 10 to the 23rd atoms is just Na. So N subscript A is equal to 2 times 10 to the 23rd. And here I'm just going to put particles. Okay, because like I said, it can be anything. It's much easier to write N subscript A than it is this entire number and every single thing that you do. Alright, so keep it simple, right? So what is a mole? Well, the mole is not, as this picture states, it's not 2 moles in 1 liter. Later on we'll discuss this more, but this is a play on words, because 2 moles per liter means there are something later on which we say 2 moles per liter. This is a unit of concentration that we'll know later on to be called molarity. And it has nothing to do with moles. It's just a funny picture that I found. Alright. So remember, like I said, a mole can just be 6.022 times 10 to the 23rd things. and we can write that also as Na, so Avogadro's number. Okay. So the mole. The mole helps us make a connection that we can define as a counting unit. All right? It is abbreviated as MOL. And a mole is simply a unit that defines an amount of something. So much like the way that a dozen defines 12. So if I have a dozen eggs, that means I have 12 eggs. Or if I have a gross, that is a dozen, that means I have 144 things. Okay? So let's work this out. Let's do a couple practice problems. All right? So first off, how many dozens are there in 1 mole? Well, first off, recall, what is 1 mole equal to? This is Avogadro's number, which is equal to 6.022 times 10 to the 23rd things, right? Okay. So we need to figure out how many dozens are in 1 mole. Well, we need to know what to start out with and what we want to end up with. So we just need to figure out how many dozens are in 1 mole of something. So 6.022. Then we go to EE. If I can find it. Here it is. It's EE. So we go second EE to the 24. And then we're going to make this a little bit easier. Second insert. And we'll go to the end. It's always good to make sure that you enclose your operations in parentheses. We're going to divide that top number by 12. Okay. Enter. And so it tells us that there are 5.01333 going on forever. Dozen in that number. Okay. What about if we divide gross? How many gross are there? So that means we're no longer dividing by 12, we're dividing by 144. So 6.022. And when we come back to our calculator, can we go back up? Yes, we can. Nope, looks like I gotta do it all over again. And that's 4.1819. To 20 seconds. Okay. That's basically it. You know, we're taking this really large number and dividing it by some smaller numbers, so we should end up with reasonable numbers like we're getting here. Okay, so this is just a simple mathematical problem I just want to show you all. Okay. So we've been able to go from, defining, atomic masses. And that's all well and good, but now we need to move on to being able to build up molecules and figuring out from molecules how much those weigh And so that's where we get to here, molar mass. And we're defining atoms, molecules, and then being able to define, molar mass for these particles. So like we said earlier, the atomic mass of a single atom of an element is the average mass of a single atom in atomic mass units. All right? So like we said, one atom of fluorine is 19 AMU, therefore 19 AMU is how many AMUs there are per atom of fluorine. All right? Where this changes now, like I said, we want to deal no longer in AMU, we want to do molar mass in grams. So molar mass lets us define the relationship of the mass of the atoms in grams. Okay. So it says that 1 mole of an element corresponds to the mass of a mole of atoms in grams. So that means in this case, for every 1 mole of fluorine, this is equal to 6.022 times 10 to the 23rd atoms of fluorine, which is also equal to 19 grams of fluorine. All right, that's what we're doing here. We said that 1 mole of fluorine is equal to 19 grams of fluorine, and when we make our conversion factor, we're saying that 19 grams of fluorine exists in 1 mole of fluorine. So this right here is pretty important. Like we said, this is our conversion factor. Okay. So let's work this out. We want to know we want to figure out how many AMU (2 grams) and finally 2 moles there are of this material. Okay, so this calculation is set up for you here, but I like to redo it. That way we can start it from scratch. So we're going to go from AMU, convert that to grams, and finally from grams we're going to go to molar mass, which is grams per mole. All right. So we start off with 19.00 AMU of fluorine per 1 atom of fluorine. Then we're going to multiply that by the relationship of AMUs to grams, which we said earlier is 1.661 times 10 to the negative 24 grams of fluorine is equal to 1 AMU of fluorine. And then finally we're going to do 6.022, so we're going into a new conversion factor, which is going to be Avogadro's number relationship to moles. Okay. For 1 mole of fluorine. So remember, measurements have a number and a unit. The units, we can treat them exactly as our numbers when we do addition or subtraction, multiplication and division. All right. So here are a couple of things to keep in mind. Here we have AMUs of fluorine, AMUs of fluorine. Here we have grams of fluorine, and over here we have atoms of fluorine and atoms of fluorine. Okay. Well, keep in mind, right? When we're going to do 1 divided by 1, this gives us 1, right? Or if I do 2 divided by 2, this still gives us 1. If I were to take AMU of fluorine and divide it by AMU of fluorine, this also gives us 1. That means that these things reduce out, right? So what the heck does that mean? That means that they go to 1, so they go away, right? So AMUs of fluorine go away, atoms of fluorine go away also. So the only units that we are left with are going to be grams of fluorine and moles of fluorine as the denominator. Right. Well, there's still one more step, and I like to take this step by step. It means that it's a little bit more, not tedious, but more drawn out, okay? Alright. So whenever I do this in the calculator, I like to do it in the long way. So I go 19.00, then I'm going to multiply that times 1.661 times 10 to the negative 24, and then I'm going to multiply that times 6.022 times 10 to 23. Remember, we still have our units, and those units are in the back, grams of fluorine. Once I do all that, I get some number, and I'll put that onto the top, okay? But then let's arrange these down here. So I have, this one's pretty easy. This one's going to be 1 times 1 times 1 mole of fluorine. And I do this the long way so that way you all can see exactly what's going on, right? So units down here are moles of fluorine. So let's calculate this out. So I have 19 times 1.661 second e to the negative 24 times 6.022 to the 23rd power. Enter. Well, that should come as no surprise. The slide had already told us that we were going to get 19.00 grams for every 1 mole of fluorine. So when I multiply this top part all the way across, I come up with 19. The bottom part is just 1, so we can rewrite this a little bit more cleanly. This is 19.00 grams per mole of fluorine. And that's our final answer.